Rahim. Today we will talk about a very important topic in MIMO communications. The topic is SVD. SVD stands for Singular Value Decomposition. So this is the lecture number 23 for week 11 on online courses of Advanced Wireless Communication at IST at master's level. So what is Singular Value Decomposition? So far we have studied different perspectives of MIMO systems, and we saw different types of receivers: zero forcing receiver, maximum ratio combining receiver, maximum ratio transmission, transmit beamforming, and we also talked about Alamuti in the last lecture. So we will now see a unique decomposition of MIMO wireless channel. This decomposition is called singular value decomposition. This is not the only type of decomposition in the literature, but we also have another decomposition which is called eigenvalue decomposition, which is only for square matrices. Now singular value decomposition gives you an idea of the character of the MIMO channel, and it helps in analyzing the behavior of the MIMO channel. Eigenvalue decomposition is for square matrices, but singular value decomposition is for all matrices, applicable to all matrices, which could be tall or which could be broad. So what does SVD do? It gives valuable insights into the properties and behavior of underlying MIMO channel. So if we have a channel matrix containing channel coefficients, and the dimension of the channel matrix is R cross T, and in general R is greater or equal to T. So the singular value decomposition decomposes the channel into three matrices. The first matrix is the U matrix, the second matrix is the E matrix or the diagonal matrix, and the third matrix is the unitary matrix. We will see the details of what are the properties of these matrices in the next slide. So how we decompose? The decomposition is given as such. The U matrices contains columns of U vectors. The V matrix contains columns of V vectors to the power h, or V Hermitian rows. So U matrices are columns and V matrix is a group of rows. So the dimension of U matrix is R cross T. The dimension of the V matrix is T cross T. And we have a matrix in between, which is the E matrix. It has a dimension of T cross T. So the total dimension when we multiply these matrices would be R cross T. So this is decomposition. We have a single matrix of dimension R cross T. It is decomposed into three matrices, namely U, E, and V, with these dimensions. So overall dimensionality of the multiplication of these three matrices is preserved. So let's look at the properties of this U matrix. U matrix contains columns of orthonormal vectors. So here is a mistake. So we have Ui Hermitian multiplied by Uj, not Uj Hermitian. So you can delete this H here and H here. The important property is of orthonormal. Orthonormal property is different from orthogonal property. All orthonormal vectors are orthogonal also. Orthogonal and orthonormal properties are similar, but orthonormal has one separate property, that if you multiply Ui Hermitian with Uj, that would be equal to 1 if I is equal to j. That means if you multiply the vector by itself and taking the Hermitian, then it would be, answer would be equal to 1. And this is the orthogonal property, that the columns of this matrices, if they are multiplied, different columns are multiplied with each other in this fashion, the result would be equal to 0. So all orthonormal vectors are orthogonal also. The columns Ui are given as follows. So if you multiply U H complete matrix and take the Hermitian of it and multiply it with U, you will get this thing. And each element, if you multiply it together, when I is equal to j, then you will get at the diagonal Ui squares and U2 squares and UT squares, the off diagonal elements would be multiplied with each other, and because these are orthonormal, so they would be all zeros, and the diagonal matrix, because they are orthonormal, they would be equal to, all the diagonal elements should be equal to 1 following this property. So when you multiply u to the power h with u, this is basically given as identity matrix. So this is the property of ortho being orthonormal, and it is saying that the columns are orthonormal. So what is the other matrix V on the right side? If we multiply V Hermitian with V, that would be equal to multiplication of V with V Hermitian, that is giving you I t cross t. So V is also a unitary matrix. So both are giving the result as a unitary matrix. Now let's look into the detail of the middle matrix, which is basically the E matrix. E matrix is a diagonal matrix. The singular values should be non-negative, that is sigma 1, sigma 2 to sigma t should be greater than equal to 0, and the number of non-zero single values should be equal to the rank of the matrix. Singular values are arranged in decreasing order of magnitude, that is sigma 1 should be greater than sigma 2 should be greater than sigma t here, depending upon what is the value of t. So let's see an example of SVD of a simple SIMO case in which we have 1 transmit antennas and 2 receive antennas. So R is greater than T, and let's assume that H matrix is equal to a simple column matrix with elements 1 and 1, and try to decompose this into SVD. So if we decompose this into SVD, we normalize it and divide it by a square root of 2. Then the middle matrix would be square root of 2, and on the right side we can just multiply it with a matrix with only one element, which is a scalar. So this is the V matrix, and we can see that if we see the property of this V matrix, it should be V Hermitian multiplied by V is equal to V multiplied by V Hermitian, should be identity. Yes, it is an entity. So let's take the U matrix. If you multiply U Hermitian with U, that would also be equal to 1. So the middle matrix is basically sigma 1 is equal to square root of 2, so that is greater than 0, so it has a full rank, it only has one eigenvalue, so that is a perfect SVD decomposition. It has all the properties of the SVD decomposition. Let's take another example number 2, in which we have H matrix like this, 2 zero elements and diagonal elements 1 into square root of 5. So let's decompose this. If we decompose this in this way, so we have U matrix and we have me matrix. We just multiplied the left side and the right side with identity matrix. So this is not a valid SVD. The reason is that this one is smaller than under root 5. So as we discussed below, the first eigenvalue should be greater than the second eigenvalue. U is equal to I, this property holds. V is equal to I, that property also holds. The unitary matrix and the other unitary matrix, they are both fine, but diagonal matrix does not behave as a standard SVD algorithm, so it is not a valid SVD. So what we can do to make a valid SVD? So we can decompose in another way. First, multiply this system with this system. So we can decompose this into two matrices as shown here, because when you multiply this matrix with this matrix, you get this matrix. So the order of the eigenvalues is flipped here, but again you can decompose this into these two matrices. Again the order could be reversed. This comes here and this comes here, and you multiply it with another matrix V here. So this stays like this as similar, but this is further decomposed into two matrices. So now if we see that this is a U matrix, it behaves as orthonormal columns, and this is a unitary matrix, gives identity. The SVD is valid because now the E matrix, which is a diagonal matrix which only contains the diagonal elements, it is having sigma 1 greater than sigma 2. Let's take another example in which we have h1 2 1 minus 2. If we decompose this into this form by taking the negative sign out, multiplying with the positive, and then decompose this as is given in this example, this matrix, you will have 0 1 0 1, and you will get these two matrices. Now you can normalize the columns of the matrix to make its columns orthonormal, because this is not orthonormal. To make it orthonormal, you can normalize it with the square root of 2. Square root of 2 is the sum of 1 square plus minus 1 square under root, that is equal to under root 2. So if you divide the whole matrices with square root of 2, you will get this H as such. So this is orthonormal matrix, this is unitary matrix, and this is the diagonal matrix E with sigma 1 greater than sigma 2. So this is also a very good example of SVD decomposition. So in which we basically have found out a few tricks or methods to basically decompose this H matrix.